So we want to discuss the procedure to reconcile system-level mathematical equations with circuit-level equations that give us our component values. And we started talking about this in chapter 14, but I want to take you back to the fundamentals of it. Any system, its input-output behavior, essentially we are modeling with a differential equation or a system. These are linear systems, so these are linear ordinary differential equations. And what we have is some type of set of, let's say, differentials on I that with some coefficients of our input. So this is just one side of the input differential equation, and we have on the other side our output with some coefficients okay, and we know that our, in the Laplace transform, our S really is a differential operator. So this is what our Laplace transform polynomials come from. This becomes polynomials in S that I can factor and take the Laplace transform of my input, and on this side I get the same thing, and I can factor out my Laplace transform of my output. Then you can see where we get these rational polynomials from. So if I get my transfer function, so this is my transfer function, then you can see that I get my polynomial in the numerator over the polynomial in the denominator. So that this is, and this is what everything is coming from. Is essentially from a system level formulation of differential equations for the system. And these polynomials are going to have these coefficients. Okay? And I get this. Now we go further. We go further because if you recall, the Laplace transform expresses all the behavior of the system, both transient and steady state, or also known as phasor behavior. Because you recall that S is sigma plus j omega, but if you solve for the response at the Laplace transform level, this sigma shows up in the decaying exponential. So that is a transient behavior. That's why we get away with setting that to 0 and focusing on j omega, which is the steady state behavior, the frequency response. So we set S to j omega, and instead of S, we get a frequency response. That is the steady state, what we care about. When we are looking at this frequency response, we're not looking at the transient behavior. We have put that aside. We already checked out the system from a unit step response from a stability perspective. We check all that in the S domain. And then we say, well, all that is good. Now let's look at the steady state response, and we get this transfer function on j omega, which is really the Fourier transform. And the Fourier transform is a special case of the Laplace transform when sigma is equal to 0. And now, on omega, we get all these polynomials responses for the magnitude as well as the phase, and we figure out these polynomials that may look like this, or may look like this, or may look like that. Different polynomials on j omega. So, and we get the response that we want. All the while, this is at a mathematical level, and what we have are still this polynomial, rational polynomial on j omega that has coefficients and and has b coefficients, the same ones that we had in the original differential equations. And we get the system behavior that we want, both from a transient behavior at the Laplace transform level and from a steady state level at the frequency, with a frequency response of Fourier transform. And we stop there. That's as fast as we can go. On the circuit side, with what we know from electronics, we come up with a topology. That's a circuit. And then we use Kirchhoff's laws and other circuit analysis techniques, so node, mesh, node analysis, mesh analysis, loop equations, and so forth, to come up with equations that are going to be very similar to this rational polynomial. We solve again for the input, in this case, let's say it's a voltage, for an output to input relationship, which is going to give me a polynomials, but instead of, and it's also going to be over j omega, but instead of having this a and b coefficients, the coefficients here are going to be in terms of the components. The coefficients here are going to be in terms of the components. Then by inspection, I look at these two rational polynomial relationships and I equate the appropriate coefficients that I got from the system level to the coefficients that are expressed in terms of the component values. That is what is called design equations acquisition. Because when I say that my coefficient a sub 0 is equal to some function of R1, C1, etc., now I have equations that I can use to solve for these values. Because I got this from my system response. I know what that is. So where appropriate, that is the work that I'm going to want to see from you in 2 weeks. Okay? That is the work. Let me give you a not so complex example, but more, but closer to your project. So you know that on your system side, you have to do some integration. At a point, we talked about integrating a constant, and that you wanted to, for the pulse width determination, you know that you have a pulse width 1 that needs to give you a voltage 1 out, and a pulse width 2 that needs to give you another voltage. So that's a linear relationship. So that gives you the slope that the output of the integrator must have. So that it must be the slope, and we want a linear relationship, and since you know what you are integrating, when you substitute by the pulse width, you get your equation on the pulse width. And that's all you know at the system level. But when you look at the circuit of an integrator, you know that integrator V out is going to be VI over RC T. There you have it. This is the circuit equation. This is the system equation. And this is your design equation. So here you have one design equation, and you have 3 values. You can choose what voltage you put in there. You can choose the value of your resistor and the value of your capacitor. And you have one equation. But you can come up with more equations. You know that your slope needs to be such that you don't saturate your output, because you're going to be implementing this with an op-amp. So if your slope, you're controlling the integration time with the pulse, if your slope is too steep and you have a wide pulse, you will saturate prematurely, and you won't be able to measure the right voltage. So you know that your slope must be enough to capture the widest pulse. That's another design equation that comes from the system, and also informs, because at that point is V out must be VI over RC times the widest pulse. And actually this VI would be V2. That's another equation. So again, more specific to your project, but the same idea of system level derivation, circuit derivation, and this equation comes from applying node analysis to the op-amp circuit, to the classic Miller integrator. Okay? And just equating by inspection what the part that gives you the components value must be from a coefficient perspective in the system equations. And then you get your design equations and you find the values. That is what I'm going to want to see everywhere that is appropriate in 2 weeks. And then you can make it more sophisticated for the final report, but I want to see that you have done that work when you submit. Any questions about that? All right. So let's keep going with chapter 14, and this is the kind of things that we were doing by looking at system level behavior of filters. And just rewinding a bit, we have talked about the fact that these rational polynomials on J omega could be factored into first order subsystems and second order subsystems. And the first order which we call, these first order filters, which we call a bilinear, we call this a bilinear transfer function. Looks like this. So you can see your A and B coefficients, which means that this filter, this transfer function, has a 0. So things that we look at the system level is the properties of the zeros and the poles, how that influence the system behavior, input-output behavior of the system. So this has a 0 at and a pole So that is one type of factor subsystem that you can get out of this rational polynomial transfer functions. The other one is second order.
Professor?
Yes.
For the zeros, it was A0 over omega 0, or should it be A0 over a negative A0 over A1?
Let me look. Yes. Sorry about that. So just to make the correction for the first order, that is okay. Definitely. Thank you for that, Keith. All right. So let's talk about the second order. And we call that a biquadratic transfer function that looks like this. And if we apply the quadratic equation to find the poles of this system, we find that we have the two poles and they are complex conjugate pairs. And now we can look at interesting cases of these systems, specifically because the second order, because the first order is straightforward, but the second order is more interesting. We can look at specific cases. First of all, let's look at the low pass case. So in that case, we said that the low pass filter has the zeros at infinity, meaning that the equation for a low pass filter must look like this. And we can look at, so again, at this point, all this is on a mathematical basis, and they have people that have looked at the properties of these types of systems from a mathematical rational polynomial perspective. For example, we see that we have a peak in the response if Q is greater than 1 over the square root of 2. We have also observed that we have a maximally flat response if Q is equal to 1 over the square root of 2. And then we have good roll-off. We have good roll-off if Q is less than 1 over the square root of 2. Now, I think I mentioned this last time that obviously if you wanted a filter to extract a DC component, you want that response to be flat at DC, so you would want a filter in this category. Okay? So you can get a lot of understanding by looking at how these quantities affect the behavior of the filter. And let me correct another typo here. How these quantities affect the behavior of the filter, of the low pass, because then you can do, since we're working mathematically and the response is normalized, the magnitude of the response is normalized, we can then say, well, if I really understand the low pass, then a high pass filter is simply 1 minus the low pass response. And now I have a low pass to high pass transformation. Another interesting case is the band pass case that has a response of 1 0 at DC. I must have 1 0 at DC because this is a band pass. I cannot pass the DC. I have to take that response to 0. And then over my denominator. And remember that while the zeros gives us the behavior, the poles give us the selectivity, and therefore it gives us the frequencies of the bandpass. Again, applying the quadratic equation to the denominator, we come up with these frequencies, system level again. So here you can see that for the bandpass, we have the center frequency, and then we have the bandwidth, or that term related to the bandwidth. So if I solve for the minus 3 dB bandwidth, defined as omega 2 minus omega 1, I get that the bandwidth is the natural frequency over the Q, which is called the quality factor. And the higher Q is, the narrower, you can see the narrower my bandpass is. So if I want to have a very selective filter for a very specific frequency, that type of shape implies high Q. So when a filter is very selective, we talk about a high Q filter. So now we understand a little bit about the low pass, and we can make a transformation to high pass, and we also understand a little bit about the band pass, which allows us to make an easy transformation to a notch, also called a band stop, which is really 1 minus the bandpass transfer function. There is also another organically developed notch filter that you can derive by setting or taking this transfer function but it is related to the 1 minus the bandpass case. And you can see that the zeros are at plus or minus j omega n as long as this condition is met. So you can start appreciating how we can look at these rational systems and start just defining and getting relationships for their behavior, and we can keep going from there, looking at special cases. Anything that we do and look beyond that is really special cases. So let's start looking at some special cases. the low pass Butterworth filter. This is the case where you have a maximally flat response. And let's look at the frequency response of that filter. And if you apply, or going back, equating that term to 1 over the square root of 2, you get that this relationship, and I'll explain what those parameters are because they're related to some pictures that I'm going to show you later. And what you can do as well is extending the case of these special cases of filters to higher order filters. So in this case, we have, this is not just a second order filter, this is a nth order filter that has this magnitude response. And if you find what the pole frequency is, so equating omega to WP, then your magnitude from the equation above becomes these parameters have behavioral significance, and we'll go back and look at the figures in the book later on. For example, the parameter epsilon determines the maximum variation in the passband. And when we started the chapter, we talked about what that was, and we called that a max. And so we work in dBs for the magnitude side, or the magnitude axis, and a max is always given in dB. We can say that a max is equal to any log of 1 plus epsilon squared. So you're given a max, and with this equation you can find what your epsilon is, so you can put that back into the system level. At some point you're going to come up again with some topology that is going to have its own coefficients in terms of the components, and then you equate those and you get your design equations. Okay, so again, just making a special note that this type of filter gives you a maximally flat response. Therefore, good for extracting DC. Okay. If we set epsilon to 1, then you can find that A max is the normalized 3 dB point, and omega sub p is what we call the 3 dB bandwidth at the edge. So that's at the edge of the stop band. So let's take a look at that. We're just calculating the response at the stop band frequency. Remember, this is a low pass filter, and you get this this characteristic, this equation. Stop band frequency divided by the pass band frequency raised to the power of 2 to the n, and that simplifies to
Dr. Hernandez, is A to the WS like the lowest amplitude of the characteristic of the filter?
yes. So that would be the minimum attenuation that you require at the stop band. So we're talking about a low pass filter. So it's got to have some variation that is maximally flat and maybe some here, but this here is and here we have our A max is here, but the one that we are talking about now with that equation is this one. Okay, so that would be A, this is normalized to 1 over here. Okay, did that answer your question?
It did, thank you.
All right. All right, so what else have we learned from studying these filters is that the filter order required, this is important, is the lowest end, the lowest n, because we don't want to make it more complex than it needs to be, such that the attenuation is greater than the minimum that we need. Remember that we're going to be given WP, WS, and those two define how fast we need to transition from the passband to the stopband, and we're also going to be given A max on the passband and A min on the stopband. So that's all you get from a system perspective. And now you have to come up with your equation. So here's a procedure for Butterworth filters, a general procedure. Step by step. Now you have to come up with what those values should be by the understanding of your system. So first we can, from A max, determine epsilon with the equation that we showed before, which was 10 okay? Then we can determine the filter order. And we said that that was the minimum n that satisfied So you can solve for n because you're given omega s and omega p, and you just calculated epsilon. You can solve for n. Notice that the closer WS and WP are, the higher your n. That means that you have a very steep transition, and that implies a higher order filter. So while a second order filter may have a roll-off like that, if you have, let's say, a 10th order filter, it would have something like that. So omega, oops. So those, obviously, this ratio is much closer to 1 than this. So now you have the order of the filter, and you have to check that the attenuation is appropriate, greater than the minimum that you need. All right, so now with these numbers that you have calculated, you can start constructing your system equation. You're still working on the Laplace transform domain. So step 3. You have to actually assign the poles in your transfer function. You know epsilon, and you know your passband omega. Another helpful equation during this step is the actual poles So this gives you all the different poles that you need according to the order of your filter.
What's the variable close to 2? Is that an R?
K.
Okay. Okay.
This is a K. And K K let me not confuse things. Let me just clear this. K runs from 1 to n minus 1 over 2 for n if n is odd, and K runs to n over 2 for the case when n is even. So at this point, you can determine your Laplace transform level transfer function because you have the poles and you have all the other parameters. So that's the fourth step. And then a set of factors on K, because we already calculated this, of second order systems. And then we throw in a scaling factor. So I don't want to confuse this over here is lowercase k. That's just the running index of the factors. This is capital K, that's a scaling factor. So you just calculated omega naught, and you calculated the Q's, then you can come up with your polynomials. Depending on whether, so this would be for the odd case when n is you can see here, right? That's for the odd case. And then for the case when n is even, you will have so you don't have that lonely since n is even, you don't have that lonely first order factor in the denominator. You just have a set of second order systems that gives you your set of complex conjugate poles. That's where this second order factors come from. Okay? So this is for even. All right, so that covers the Butterworth case and the design, how you get to the system equations. We'll see later how we take it from the other end by starting with the topology and equating the these coefficients to the equations or the coefficients in the equations that we get from the topology by applying circuit analysis techniques. So let me stop here after this treatment of the Butterworth low pass filter, which is a very important case, and switch back to discuss some pictures in the book that have to do with everything that we have discussed. Okay, so again, this has to do with the magnitude response of a second order factor or filter in the different cases for the value of Q. So a Q that is higher than 1 over the square root of 2 tends to give you this peak over here. Okay. If you have your Q equal to the 1 over the square root of 2, then you have that maximally flat behavior. At some point, you roll off. And then if Q is less than 1 over the square root of 2, you have a continuous roll off. For the bandpass case, let me For the bandpass case, you have this, your center frequency, the sideband frequencies that gives you the bandwidth. So we discussed how that was equal to omega naught divided by Q. Your maximum response, the 3 dB bandwidth points at the band or sideband frequencies, and these are the equation that I essentially wrote for those frequencies. So these pictures that I highlight in the book are the ones that you should be, of course you should be reading the book, but specifically spending time with these figures and understanding them and relating it back to the text, what they're saying in the text. We also have the notch case. This is not the one that you get just by subtracting the bandpass transfer function from 1. This is actually a specific type of notch filter that gives you some pass on the low side, but then it gives you a notch rejection on the stop band. So that's when, after I mentioned the 1 minus the bandpass, I also derived and wrote the expression for a transfer function for a notch filter. It is this response. And then we discussed the Butterworth filter and the derivation of its transfer function procedurally. So here we have the normalized response and the meaning of the term epsilon in relationship with the omega for the passband. This is an interesting figure that shows, for the normalized case, what I mentioned, and it shows the steepness of the transition from the passband. So here's the passband to the stop band as a function of that ratio or as a function of the ratio of frequencies, and also the relationship to the order. So you can see that the higher the order, the steeper the transition. In the range of up to 2, meaning that the frequency is twice the passband frequency. So that gives you some idea on how the filter order impacts the transition from the passband to the stopband. And again, the response, the magnitude of the response is normalized to 1. And finally, one of the things that we mentioned when designing Butterworth filters was the distribution of the pulse. So you can see here for the different cases how the poles are distributed in relationship to n. So for the case when n is odd, you have this real pole, and then you distribute the rest of the pairs in complex conjugate pairs. So this is the case for a third order filter, in which you have these 2 poles here in pair and a real pole. And this would be a fourth order filter, in which case n is even and you don't have the real pole. You have basically 2 pairs of complex conjugate poles evenly distributed. And what is shown above is essentially the general, this is the general case. This is order 2 here. So you have essentially 2 poles evenly distributed. You can see 45 degrees on each segment here. And you can see the other case for the other orders. So that gives you an idea. This picture not only gives you the width of the interval, what section of the circumference is between the poles. So you can see that this over here is always pi divided by 2 over n, same as down here. And then for the rest, the spacing is pi over n. And that's how you distribute the poles. That's essentially the rule. And you can see examples for 3 different orders where you have 2 even cases and 1 odd case. So this is a very helpful figure in the book, okay?
Dr. Hernandez,
Yes.
would it be helpful to generate these pole graphs for project?
Yes.
Okay, thank you.
That'd be great. Yes, I think that'll give you, I mean, you're going to have to, according to what we discussed, you're going to need a filter to extract DC, and I just gave you We just went through the procedure of designing a filter for the best type of filter for this extracting DC. Once you set the parameters of your A's and your omegas, then you can embark in this procedure to design what kind of filter you're going to end up with to meet the requirements of the system. So today's lecture is very applicable to your project.
Thank you.
Thanks. Any other questions at this point? All right. So I'm going to stop here. Let me stop here.